Alright, so today we are looking at how rates or related rates can be associated with our differential equations. Alright, and particularly in terms of application kind of questions. So the theory stuff in terms of what you had to do in the process of solving we've done before. So we'll just do a couple of examples. One fairly straightforward and then one more involved. So differential equations with related rates. Alright, so first up, example, all the variables x, y and t. It is known that dx dt is equal to tan t, and also it is known that y is equal to 3x. Alright, so we've got three variables, x, y and t, and they're linked together by this stuff here. Alright, so first part says, part A says find dy dt as a function of t. Alright, so whenever it says it's a function of something, that just means that's what's in the variable that's in your sum that you've got. And then part B, we want to find the solution to the differential equation. Alright. So solution. Part A, so it's asking us to find dy dt, and what we have been given is we've been given dx dt. So if we use the chain rule, then the second part dx dt, and so that's going to give us the dt on the bottom. Now we need the dy on the top, and then of course we need the dx is the thing that is linking those, so we need our dx down here. Alright, so here's our related rates. So we know dx dt, we've got something about y in terms of x, so we can find dy dx. And so dy dx would simply, I think, be just 3, wouldn't it? And so we've got 3 times tan t. So it's asking for dy dt as a function of t. Well, this is dy dt, and it's got t in here on the right hand side, so it is a function of t. All right. So part B asks us then to solve that. Part B, we're going to solve that. So dy dt equals 3 tan t. So if we've been asked to solve that, what that means is that we need to get y equals. So to get y equals, what might we do? Anti-differentiate, yep. And we're going to anti-differentiate with respect to t. So we'll have y here, and on the other side, put the 3, it's a constant, put it out in front, and t dt. All right. So tan, got to anti-differentiate it. Any thoughts? Tan's an interesting one because it's not on the formula sheet. But what do we know about tan? Sine on cos. So sine t on cos t. All right. So now we're going to do substitution, aren't we? And u is going to be? Cos, yes. Got one on the bottom. All right, so this is a useful reminder. It's tan, to get tripped up on tan. We're just doing tan. It's not on the formula sheet, and you go, oh, what do you got to do? All right, so you need to rewrite it as sine on cos, and then the bottom you let u equal cos t, and that's handy because then the u dt, of course, is negative sine t. All right, and so we're going to then that means that dt would be du on negative sine t. All right, so let's make those replacements. So we've got sine t up here. We've got u there. We're replacing dt by du on negative sine t. So sine t's cancel. Bring the negative out the front. We've got 1 on u du, which is log, yep. Log to the base e magnitude of u plus some constant. And don't forget, make our replacement back. Magnitude of cos t plus some constant. All right. Next example. So this next example's in the textbook on page 400. This is it here. 21. All right, this one's a bit more involved. And we've got a few things. So we've got an inverted cone, height h centimetres, radius length r. So it looks like this. Height h, radius is r, so if the radius is r, then the whole way across here is 2r. And they're in centimetres, all of them. It's being filled with water which is flowing from a tap, so we've got water coming in, flowing from a tap at k litres per minute. Alright, so if we're talking about that, then that's going to be dV dt. The volume, litres is volume, yes. The depth of the water in the cone is x centimetres at some time t. So if I wanted to put some water in there, so here's some water in here, and the depth of that water is x at some time t, and we'll get to that in a minute. All right. So, first of all, before I go any further, I've got something that I need to, well, I will reconcile now before I go any further, and that is our volume here has been in litres, but our dimensions that we're told about our cone is in centimetres. All right, so we can figure out the volume of a cone, because it's a cone, so the volume of a cone, and this is on your formula sheet at the front, those things that you always wonder why are they there. All right, so it's 1/3 pi r squared h, so we know the volume of the cone. Right here we've got the water coming in at k litres per minute, but our dimensions here are in centimetres, so if we're going to use that, then we'll end up with different units. So we need to bring them together, and we can bring them together because 1 litre is equal to 1,000 cubic centimetres. So my rate of changing my volume of water, rather than just K, if I then put it as dV dt equals 1,000 K, that's now in centimetres cubed per minute. Alright, so K is in litres per minute, times that by 1,000, because there's 1,000 cubic centimetres in a litre, and we've got 1,000 K. Alright, so we'll get to that. Alright. So there's that. What else do we know here? So we can work out, so we've got the volume with time, and what we are asked to do, in the end, we are asked to construct an appropriate differential equation for dx dt. So we need to get dx dt in there in some way or other. All right. Now, the other thing that we have is we have this particular cone, and we've got radius and we've got height. Now, this x is referring to the height. So what we need to be able to do is we need to be able to, because radius is in there, if that's there is x, we need to know what this radius is for this particular height x. And so we don't know what that is there. Call it y maybe, if you like, call it y. Now the reason I'm going to call it y is if I now have two triangles here. Alright, so I have two triangles. Like this little one down here, which filled up a bit of the cone, and then I've got the whole cone. And what do I know about those two triangles? Is that they are similar. So this side up there is R on the big triangle, and that's H. So because they're similar, the ratios of those sides have got to be the same. Alright, so from our triangles, the ratio of the sides, so that length divided by this length, so the x, how deep it's filled compared to the whole depth of our cone, and the ratio of the radius of this circle here, where it's filled up to that there, have got to be the same because they're similar triangles. Now I've called that y over r. Okay, so what I want to do is I want to get this y by itself, so times both sides by r, and so y, which is the radius that it's filled up to, and the depth is x, is x times the radius of the cone over the height of the cone. So, my volume of the whole cone, so again we're talking about this blue bit down the bottom here, this volume as compared to the, not want the whole volume because I want to know what the volume is at some time. Alright, so we've got this at the moment, whatever time this is, we've got the depth of x and a radius there of y, so I can find then the volume, so the volume of water in it. Will be a third, will be pi. Now the radius of this depth here, so we're talking about this depth x, the radius here is y, which is this stuff, x r on h squared, times by the height, and the height of the water at that time is x, of course. So, the volume then would be 1/3 pi. When I square this stuff here, I'll have x squared, r squared, h squared. Got another x out over here. So it's going to be x cubed here. So r squared, x cubed on h squared. Alright, so got that stuff. So the volume, the depth is h, is that in comparison to the whole cone. The x dt, so somehow Well, with this volume that I've got, I can get dv dx from this volume. I've got dv dt, and I need dx dt. So let's have a think about that. So dx dt, need the dx up there, need the dt down here, and the thing that's going to link them together is the v, the volume. So dx dv, dv dt. So the dv dt, we've got that. We've got the volume in terms of x. So if we differentiate that and flip it, we'll be right, won't we? All right, so when we differentiate, you get that. Written a little bit messily. What do we notice? We notice that the third and that 3 cancel each other out. So, I'm going to run out of the space down the bottom here, so we have to rub this off here and go up the top here. So now, let me neaten that up. dv dt is equal to, I'm just going to write it as a single fraction here now, pi r squared x squared on h squared. All right, anything so far? No? All right, over here we need dx dv, so, sorry, shouldn't we have t there, should I? It's x. Getting ahead of myself. Over here we've got dx dv, so we need to flip both of those. So there we are. All right, I think we're now ready to come up with our expression for dx dt. So dx dt is dx dv, which is the h squared over pi r squared x squared, times dv dt, which was the 1000k, wasn't it? What I'm going to do is put all the things that are fixed together. So things that are fixed, remember this cone is, the height of that cone is fixed. The radius of that cone is fixed. The bit that changes is the depth of the water inside it. All right, so if I put all the things that are fixed all together, 1000k, the h squared is fixed, it's the height of the cone, the pi is fixed, the r squared is fixed. Times 1 on x squared. All right, so now we need to solve that. Now, when we look at what we've got, our variable is x. over here we've got dx dt. So to work with our variable x and then differentiate with respect to that, we need to flip it. Yep, so we need to flip it. So let's flip it. dt dx pi r squared 1000 k h squared times x squared. Yes? Alright, and then we've got that, and we've got to anti-differentiate. So remember, as I said before, even though this has got R, H and K in it, those three things are fixed. Alright, so the R and the H are the dimensions of our big cone, so that's fixed, that doesn't change. And the K is the rate that the water's coming in, again that doesn't change, so we consider all of this to be a constant. Alright, so what's changing is the water, the volume of the water, the depth that the water is. That's what's changing, not the cone. The cone stays the same size. The amount of water that's coming in stays the same. So effectively, they're constant. We don't know what they are, what those numbers are, but they're constant for the sum that we're doing. Alright, so if that's the case, I can put all of that stuff outside the front. And we're just anti-differentiating x squared with respect to x. And so that would be, when we did that, it would be x cubed on 3, wouldn't it? Alright. I'll get rid of this over here now, finish with that. Alright, now I'll just neaten this up a little bit. It's this 3 I can multiply over here. So t equals pi r squared 3000 k h squared x cubed plus some constant. Alright, before I go any further, going to see, do we know information to find out what that constant is? Yes, we do. So construct the appropriate differential equation and solve it. So we're part of the way of solving it. Given that initially the cone was empty, so initially the cone is empty. So when t equals 0, x would be 0, because remember x is the depth of the water, so if it's empty it's 0 depth. And then if you put those in, what do you find out about c? 0? Alright, that's handy, because now we've got the t equals pi r squared 3000 k h squared times x cubed. Alright, so we were asked to solve it, and so the question asked us about the depth of the water at time t. Well, we've got the time for a certain depth, so we need to rearrange. And so when we rearrange, oops, I forgot a 0 there. Times both sides by what's on the bottom here, divide both sides by that, then you've got 3000 k h squared on pi r squared equals x cubed. And then we got a cube root, I hope. So you've then got then got that. Oh, I forgot my time. Got it there and I forgot it here as well. All right. Anything there you want me to clarify for you? No, quite long and involved. And, you know, if that was an exam question, it would be broken up into a number of different parts. All right. Okay, that's it then. 9F.